In this video, we'll discuss some helpful techniques to make graphing trig functions a little bit easier. First, the big idea. We know a good bit about graphing sine and cosine already. We have a good understanding of our unit circle. From here, we'll start to think about graphing when we have a circle of a different radii, maybe larger or smaller than one. We'll think about shifting the center of the circle above or below the x-axis. Perhaps think about turning on the circle a little bit faster or a little bit slower, maybe even starting our circular motion at a different point along the way. So there's some terminology involved in all of this, and this video will help you grow accustomed to that terminology as well as actually execute some problems involving graphing. So we'll start with the basics. We know already about our basic sine and cosine curve, so you can think about these as kind of like a template. We know that sine starts at the origin and it completes one full cycle 2 pi radians later, so it's back on the x-axis. But in between, it also hits the axis exactly once at pi radians. And achieves a maximum at pi over 2 radians. That maximum is 1 unit in the air, and at 3 pi over 2, it achieves its minimum of -1. So when we're graphing some transformation of a sine curve, we'll plot these 5 points, where it begins, where it reaches its maximum, back to its middle, down to its minimum, and where it comes full circle, but the coordinates might change. And that, of course, is template for the graph of sine. Meanwhile, for cosine, it's a little bit different, not entirely different. Here, let me make sure I spell that right. For the cosine curve, the main difference is it starts at its maximum point. So at an angle of 0, cosine is 1, and it's 1 again after a full 2 pi radians have elapsed halfway through its cycle. At pi radians, it reaches a minimum of -1. And a quarter way through its cycle is where it reaches its middle. So x-intercepts at pi over 2, and then another here at 3 pi over 2. Okay, so once again, whenever you're graphing a basic sine curve or a cosine curve with some transformation involved, you're gonna have those pictures there in your head. All right, so some definitions. We'll start with the midline of a sine or cosine curve. It's simply the line that it wraps around. So when we think about our standard sine or cosine curve, you can picture it wrapping around the x-axis, kind of like a vine climbing out along a branch. We can adjust the midline, this line that I've drawn here, this dotted line that it wraps around, by simply adding or subtracting a constant outside of the sine or cosine function. I'll show you that with an example. Suppose you want to graph sine theta plus 2. That's not too hard to do. So I'll set up a y-axis here and an x-axis there. And I'm going to draw a dotted line at y equals 2. This is my midline. This is the line that this sine function will wrap around, just like that. And suppose, let's see, we know that sine always rises 1 unit above its midline. So this sine curve will go up to 3, and it always falls 1 unit below its midline. So it'll go down to 1. And on the x-axis, I'm going to put pi over 2 right here. So every 3 units will be 90 degrees or pi over 2. I'll put pi here. 3 pi over 2 will go there, and 2 pi will go here. Okay, so it's technically a scale of pi over 6, but you can see it's spaced out in pi over 2s. Every block is pi over 6, that is. So when I'm sketching this function, I just take my sine template and say start at 0, start at its midline, which is now 0, 2. Go to the maximum point by pi over 2, come back to the middle, go down to the minimum point, come back to the middle. The sine curve wiggles just like that. So you can really see it a quarter turn at a time. that's really all there is to it. One last thing I'll point out there is for this graph, the domain is still all real numbers, though I'm just graphing it on an interval from 0 to 2 pi. And the range is no longer -1 to 1. Both of those endpoints have increased by 2 because, well, I added 2 to the y values. So the range is from 1 to 3 inclusive. Another definition, that's amplitude. The amplitude of a sine or cosine curve. This is the same idea as a vertical stretch or vertical compression. So here's a cosine curve, and I'm sketching the midline on here so you can picture it. The amplitude is defined as the distance from the midline all the way up to the maximum. So there is my amplitude. You can also picture the amplitude here as the distance from the midline to the minimum. It is symmetric. The amount that it rises is the same as the amount that it falls. You could also picture it as half this distance right here from the max to the min. If you take this distance and cut it in half, you have the amplitude of your sine or cosine curve. So the amplitude is different than the midline in the sense that it's multiplied. So in this example, we'll sketch a cosine curve that has a change in amplitude. Its amplitude will be 3. And a change in its midline will be 1. So this is pretty easy to sketch. Again, I'll draw some axes here, right about like that. So here is 1, and I always start by drawing that midline. There's a dotted line at y = 1. This is the line that this cosine curve will wrap around. And then I need to draw a change in amplitude, or plan for a change in amplitude, I should say. So this cosine curve will rise 3 units, 1, 2, 3 units above its midline, and it'll fall 3 units below. So 3 above, 3 below. That shows me that this function that I'm graphing here, it still has a domain of all real numbers. Domain hasn't changed. And that's because I haven't changed the inside of the function whatsoever, but also because how are you going to change a domain of all real numbers to anything new with a simple transformation? Meanwhile, the range has changed from -1 to 1 to -2 to 4. Right? So in sketching this now, I just have to think about my cosine template. Cosine begins full. That means it begins at its highest point. Normally that's 0, 1, but here my highest point is 0, 4, right? 3 units above the midline. And then I suppose I should put a little scale on here. I'll use the same as before. Here's pi over 2, here's pi, here's 3 pi over 2, here's 2 pi, right? And then I just say my cosine curve will begin at its maximum point. By pi over 2 radians, it'll return to its midline. So be careful here. Make sure you put a point on the midline and not on the x-axis. Right? The x-axis has been shifted up by that +1. So at pi over 2, we should see a value of 1. And then halfway through the cycle, the cosine curve hits its minimum, and its minimum is -2, 3 units below the midline. Comes back to the midline by 3/4, and then full circle back where it started by 2 pi. And I can just connect the dots here to see each quarter turn on the cosine. There it is. And that's all there is to it with a graph of 3 cosine plus 1. Another definition, a sine or cosine curve that has been shifted horizontally is said to have undergone a phase shift. So let me explain this a little differently. So right now we're looking at a template for a sine curve. And what I'm going to do is on top of this, I'm just going to sketch a cosine curve. So notice here that there's a cosine hiding inside of sine, right? Because that makes sense. Sine and cosine are just horizontal shifts of each other. But what I'm saying here is I have a sine curve, and if I think about shifting that over a little tiny bit, I could have a cosine. Or if I had a cosine, I could shift it over a little tiny bit and I'd get a sine curve. So let me just maybe draw axes here and here, right? So the question that might be relevant is how far would I have to shift a cosine curve so that it fell lockstep with a sine curve? That's a pretty easy question to address here. You can see at pi over 2 radians, my sine curve reaches a maximum and begins a cycle that looks like cosine. And so I suppose I could say if I took a cosine and took the angle and just shifted it by subtracting, because I want to move the cosine to the right. So I subtract, just like with your other transformations, by just that amount, 92 degrees, not 92 degrees, 90 degrees, pi over 2 radians. If I did that, I would end up with exactly sine of theta. It would fall in lockstep with the sine. You could also say this the other way around, where if I took the sine curve and shifted it to the left by adding pi over 2 radians, it would look like a cosine curve. Right? Phase shifts, you'll see, are useful for things other than just switching from a sine to a cosine. Sometimes you'll have some sort of motion that will begin a little bit out of phase, and that's what we'll need the phase shift for. So here's an example. One thing to note here when I'm doing a phase shift, and this example has a change in amplitude, a change in the midline, but also a change in the phase here. It's shifted to the right by pi over 3. What I'll typically do is I'll typically do it in degrees rather than radians. Instead of minus pi over 3, I'll think minus 60 degrees. It makes everything so much easier to think in terms of degrees and how it relates to your standard sine or cosine template. So let me show you what I mean. So here's a y-axis, and here is an x-axis, like that. All right, and I'm going to start by drawing a dotted line at -1. -1 is my midline. So here's the line that this cosine curve is going to wrap around, just like that. And then I'm going to recognize that this cosine curve will rise 2 units above. So it'll rise all the way up to 1 and fall 2 units below, down to -3. That is to say, we're going to have a domain of all real numbers, but we're going to have a range from -3 to 1. If you haven't noticed, it's really helpful to think about the range and the y-axis ahead of time before you start graphing. And then the only other thing that I need to do is I need to think about shifting this 60 degrees to the right. So normally I would do, here's my scale in degrees. I would say, what were we saying? Pi over 2, pi, 3 pi over 2, 2 pi. So if I were to do that in degrees, it would be, here's 90 degrees, here's 180 degrees, here's 270 degrees, here's 360, right? I'm thinking about moving all of these to the right by 60 degrees. And so that means you just think about your x-axis divided, every block is 30, right? So cosine would normally begin at its maximum point right on the x-axis. It would normally begin right here. But now that needs to get shifted over to the right 60 degrees. So that point needs to move over to right here instead, right? And the whole curve needs to go along with it. So after moving that point, I'll just finish everything up. Normally it takes cosine a quarter of a period. It takes it 90 degrees to fall to its midline. So right now I'm at 60, 90 more degrees would bring me to 150, right about there where it hits its midline. And then 90 more degrees, 3 more blocks, if you're counting blocks, to fall to its minimum point of -3. And then 90 more degrees to come back to its middle. And then it would take 90 more degrees to reach its maximum point. Right? So if I just connect the dots here, I see one full period of cosine, right? Sometimes your directions you'll see will be to graph a full period. Other times you'll be asked to graph on the interval from 0 to 360. So you kind of have to pay attention to the directions for this. Here, if I wanted to graph on the interval from 0 to 360, all I'd have to do to complete it, because I'm just about there, is figure out what this bit from 0 to 60 degrees looks like. So maybe calculate the y-intercept. And this is a good opportunity to point out how easy that could be to do. If my equation is y equals 2 cosine of theta minus 60 minus 1, I could simply plug in 0 if I want to know what the y-intercept is and work it out. I get y equals 2 cosine of -60. We've mentioned previously many times that cosine is an even function, in which case I can ignore that negative. And then using unit circle values, you know that cosine of 60 is a half, and you can see that the y-intercept is actually the origin. And so if I wanted a graph of this on the interval from 0 to 360, it might just look something like that, right? It starts a little bit above its midline, hits its maximum at 60 degrees because of that shift, and then does its thing the rest of the way. One last set of definitions. The period of a sine or cosine curve is the length of one complete cycle. Meanwhile, the frequency of a sine or cosine curve is the number of cycles it completes in 2 pi radians. So what you see here is 2 graphs, each with 2 functions graphed. In blue on the left here, I see my standard sine curve. And then in blue on the right here, I see my standard cosine curve. All right, assuming that they reach a height of 1 and depth of -1, of course. And then I see on the left there another graph in red that looks like the sine curve, but you see that it does its thing more frequently. What I mean by that is from 0 to 2 pi, this red curve completes 2 cycles. That means that this red curve has a frequency of 2, completes 2 cycles in 2 pi radians. You'll also notice that it completes its cycle. It does its thing all the way up and all the way back down, back to where it started. It completes its cycle by pi radians. That means the period of this red graph is pi. The equation for this red graph is y equals sine of 2 theta. The multiplier of the 2 on the inside essentially just makes the angle measurements go through twice as fast. And what that means is the curve completes cycles twice as frequently. So that means they finish cycles every pi radians and get to 2 cycles in 2 pi radians rather than just 1 cycle in that time period. When we look on the left with cosine, I see a curve that looks stretched out horizontally. You see it takes a full 4 pi radians, this red graph on the left, to complete its cycle. That means the period of that graph is 4 pi. The length of its cycle is twice as long. But you'll notice what that also implies is that this red graph only gets halfway through its cycle by 2 pi radians. It only completes half a cycle in that standard. And that tells me that the frequency of this red graph is a half. Its equation is cosine of 1/2 theta. And to summarize this idea, like maybe a little more concretely, the big idea is we have these 2 terms that tell us about how frequently the sine or cosine curve completes a cycle and how long that cycle is, that these two ideas are linked together. And they are linked together according to this equation. Frequency is equal to 2 pi divided by the period. And when I say vice versa, that means if you were to solve this equation for period, you get period is 2 pi divided by frequency, because they are just inversely related. Like if y equals 1 over x, then of course x equals 1 over y. So knowing the frequency is enough to know the period, and knowing the period is enough to know the frequency. One more thing to that point is the frequency is a rate measure, whereas the period is a measure of length. So if I tell you the period is, 6 pi units long, then the frequency is asking how many cycles does it complete in the standard 2 pi? How frequently does it complete a cycle? And 2 pi divided by 6 pi gives you a third, so you know how many cycles it would complete. I said one last definition, but I forgot that the slide was here. A sinusoidal curve, that's fun to say. Sinusoidal is a transformation of a sine or cosine curve. It's going to have the same shape as sine or cosine, but with a change in all of these terms we've seen so far: amplitude, frequency, phase shift, and or possibly the midline. So a sinusoid will look like this for some parameters a, b, c, and d. A times sine or cosine of b, x minus c plus d. So just to make this clear, the amplitude is this multiplier here. The frequency is this multiplier right there. Notice the period does not show up in the graph at all. However, if you want to know the period, just use the formula, 2 pi over the frequency. Phase shift is right here. Notice that we need to factor out so that we can see the phase shift unaffected by a potential change in frequency. So you factor out, not out of the sine function, but just out in front of a set of parentheses there. And then lastly, the midline is on the end. Well, it's added on, not always at the end. So we'll look at one last example here where we'll try to put all this together along with a few properties that we know to sketch a graph of 3 sine negative 1/2 theta minus pi plus 5. Okay, so as it is right now, graphing this I think would be a pretty annoying task. One thing that you can do quite often is you can try to simplify. You can simplify the function a little bit before before you start to graph it. So let me show you what I mean by that. So I noticed that they did not factor out the frequency here in the middle. So I'm going to start by doing that. So I can see how big is the phase shift. So I'll factor out negative 1/2. And that leaves me theta plus 2 pi. And then plus 5. Okay, so that's super helpful. And the reason that that is so helpful is I now see that the phase shift is 2 pi radians. And we know that sine and cosine repeat every 2 pi radians. That's their period. So shifting a sine curve to the right by 2 pi or any multiple of 2 pi is actually kind of useless because it's going to look like the sine curve all over again. So this will be equivalent to 3 sine negative 1/2 of theta, no phase shift needed, plus 5. There's one more change that I can do that will make things super helpful. Right now, it looks like the frequency is negative 1/2, and that's kind of confusing to think about what it would mean to have a negative frequency. In fact, all these terms, amplitude, frequency, period, they all are positive values. So it would save myself a lot of trouble if I think about pulling this negative out in front of the function. Now, the reason that you can do that, if you think about it, is because sine is an odd function. If I had a cosine curve, cosine's an even function, I would just ignore the negative sign. I would just graph positive 3 cosine of 1/2 theta. Right? So now I'm looking at graphing this one right here. And so one other little thing that I should point out, my amplitude is 3. I do have this minus sign out front. All that means is instead of thinking about your sine template, that looks like this, goes up and then down and then back, we can just picture a negative sine template, which is a graph that would go down and then up and then back. That minus sign on the outside is just going to kind of switch our template around. All right, so I'm going to start with a shift here, a midline change of 5 units. So it's right about there. It's my dotted line. This is the line that the negative sine curve is going to wrap around. And then, so that's 1, 2, 3, 4, 5. And then I need an amplitude of 3. So this better rise 3 units above, just enough room to do that. And 3 units below. So that means this sine curve is going to wiggle between 2 and 8. That's the range of this function from 2 to 8. And then lastly, I'll just mark off here some different values. All right. Before I was listing these as pi over 2, pi, 3 pi over 2, 2 pi. But what I notice that's of critical importance here is that my frequency is a half. And so if I mark these as pi over 2, pi, 3 pi over 2, and 2 pi, I'm not going to get a full cycle in that interval. I'm only going to see half a cycle because I have a frequency of 1/2. And therefore, it's worth thinking about what the period is. In case it's not clear, 2 pi over 1/2 is 4 pi, right? The frequency is a half, the period then would be twice as big as before. So I think I'd like to mark my x-axis like this, pi and 2 pi and 3 pi and 4 pi, so that I can show a full cycle of this sinusoid. All right, lastly, it's just a game of connect the dots and finding a color that coordinates with all these colors that are on the screen. I'm going to go cyan. So sine starts at its midline. Normally it rises in its first quarter turn, but we're looking at negative sine, so it's going to instead fall first down to this point right here. And then it'll rise back to its midline, rise all the way to its maximum, and fall back to its midline. You connect the dots, and you have a graph of sine. If at any point you're unsure if what you graphed is correct, a couple things you can do. You can check it on Desmos. That's really a helpful thing to do. You can also plug in a particular value. It looks pretty clear here that pi 2 is a point on my graph. So I would go back to the function in the very beginning and say, what would happen if I input a pi right there? I'd get negative 1/2 pi minus pi is negative 3/2 pi. Sine is odd, so I can pull that negative out. That'll give me a negative 3. And if I take negative 3 and add 5 to it, I will indeed get a 2. And so this checks out. I hope these tips are helpful in graphing sinusoids.